Hey there! We've got more convergence tests. Oh my goodness. This one is the alternating series convergence test. We're also going to go over error. And so we're basically asking ourselves the question, what happens when we have a series that alternates? We dealt a little bit with this with geometric series, and I guess a little bit you could with the nth term divergence test, but not much. So an alternating series is one that usually has that -1 to the some kind of power in it, where we have signs that go from plus to minus or minus to plus, alternating positive, negative, or vice versa, all the way until we go to infinity. So it looks something like this. A sub 0 minus a sub 1 plus the second term minus the third term plus, and so on and so forth. So when you have something like that, then the alternating series test for convergence is in play. And let me point out, this test only proves convergence. To prove divergence, you'd actually have to use one of the other tests that we've used in the past. Let me show you what I mean. So we will converge with an alternating series if the terms, these guys right here, decrease in absolute value to 0. And you can actually use that statement on the BC exam to justify your answers. It's a perfect way of stating it. If your teacher's not all for that, then usually you show these two conditions, which is the limit as n goes to infinity of a sub n, meaning the non-alternating piece. You almost ignore the -1. You say, okay, it's alternating. Now we take the limit. If that goes to 0, and every successive term, the n plus first term, is less than the a sub nth term. So as we go to infinity, these terms get smaller and smaller in size. So they decrease in absolute value, meaning we ignore the negative and the plus, and the limit goes to 0. And those are the two things that you test for. I'm going to just make this statement every single time. Every once in a while I'll talk about this, but I'm going to make that statement every time. I think it's a great way of looking at it. Again, you ignore the alternation of the signs once you establish that it's alternating. Now, if we have a case where the limit as n goes to infinity of a sub n does not equal 0, that's actually the nth term divergence test that then proves that the series diverges. So just to be clear, this test again proves convergence only. Now, when do we use this? Well, we use it for a series with terms that alternate signs. Look out for that -1 to the n, or when you expand out a series, look out for the signs to switch positive to negative, or vice versa. All right, without any further ado, let's do one. State whether the following converges or diverge. So whether the following series converge or diverge, and that's for the remainder of these. Justify your answer. Don't mind if we do. So expand out. Right, just take a look at this thing, but you see that negative raised to a power, it's going to alternate. -1/2 to the 0 is 1. To the 1 would be -1/2. To the 2 is going to be +1/4, and then -1/8, and then plus ... all the way to -1/2 to the n. That is an alternating series. The signs are alternating there. Now you might notice that this is a geometric series with the absolute value of this r value less than 1, so it converges. And you could use that. That's perfectly fine. I want to use it, a familiar type series, to start with to show you how we use the alternating series test. So you can do this in a number of ways. My first way that I would justify it is since we can say the series n equals 1 to infinity, or n equals 0 to infinity, of -1/2 to the n has terms that decrease in absolute value to 0. Has terms that decrease in absolute value, I'll abbreviate that, absolute value, to 0, it converges by the alternating series test. I just spelled that with a C somehow. That's incredible. It converges by the alternating series test for convergence, by the alternating series test. Now, that has all the conditions that we've talked about in the past, right? You've got the name of the test, you've got your conclusion, you've got your conditions. You could also do it this way. You could say the limit as n goes to infinity of the nth term, but again, we're not really considering that negative part of, and you could just do 1/2 to the n, or 1/2 to the n, equals 0, and we then want to show that the n to the 1, so that'd be 1/2 to the n plus 1 is less than 1/2 to the n. And you can just state that. That is true. 1/2 to the n plus 1 has a bigger denominator than 1/2 to the n. You don't have to prove it any further. If your professor or teacher wants you to, that's fine, but most people are okay with just this. Then the alternating series converges. You can just state it that way. The alternating series converges. Again, naming the test or the type of series, naming your conclusion, naming your conditions. Either one will work. That's it. Not so bad. All right, let's do another one. State whether the following converge or diverge. Again, that being this series and the previous one and the one after that. Let's take a look at this one. We're going to justify our answer. Now, this is actually an alternating harmonic series. Let's expand it out. Expansion is your friend. Right? I've said that before. When we plug in 1 into that, we get a -1. And that's going to be of 1 over 1, so -1. The next sign is going to be positive because it's -1 squared, 1 over 2. Then -1 over 3, plus 1 over 4, -1 over 5, and so on and so forth until we get out to that nth term, -1 to the n, times 1 over n. Now we know that the harmonic series itself diverges. The harmonic series diverges, but this is alternating. And we see that the terms decrease in absolute value, right? We go from 1 to 1/2 to 1/3 to 1/4 to 1/5. Those are all getting smaller, and that won't stop. So the terms decrease in absolute value, meaning ignoring the negative signs, and they're going to go to 0 eventually. So again, I'm going to make that same statement. I'll say since the series terms, so since the terms of the series or the series terms decrease in absolute value to 0, the alternating series converges. Got to somehow work in the name of that series. All right, so we have that. Or, again, you could show that the limit, you could say since the limit as n goes to infinity of, again, we're only looking at 1 over n equals 0, and we would look at the fact that 1 over n plus 1, that's the n plus first term, is less than 1 over n. The alternating series converges. Again, naming the type of series, naming the conclusion, and the conditions. I prefer this first sentence. I love it. There's something smooth about it. Since the series terms decrease in absolute value to 0, the alternating series converges. All right, one last one for your noggin. State whether the following converge or diverge. Same instructions. Justify your answer. Okay, so let's take a look at this one. We're going to expand this one out and see what happens. So if I plug in 1 into this, that's 1 plus 1 is 2. -1 to the 2 is 1. And we plug in 1 into this, we'll get 3 over 1. When we plug in 2, you're going to get an odd power, so it's going to be minus. And now we've got the establishment of minus plus, so we don't have to evaluate that every time. You plug in 2, we get 4 plus 1 is 5 over 2. And then what we've got from there is, let's see. Well, we're going to have plus. We'll plug in 3. It's 6 plus 1 is 7 over 3. Minus, we'll plug in 4. That's 9/4. Minus, ... until we get to the nth term, -1 to the n plus 1, times 2n plus 1, all over n. And it keeps on going and going until it's gone. Now, looking at this, the terms do decrease in absolute value. This is 3, this is 2.5, this is 2.333, this is 2.25. They're going to continue to get smaller. It is a decreasing function. However, they will not approach 0. So I'm looking at that and saying, I'm not going to try to prove that this thing converges with the alternating series test, because the limit as n goes to infinity of the absolute value of this thing, meaning disregarding that, does not go to 0. That means that the infinitieth term, if that's a word, is not going to be 0. You're going to continue to change the value of this function. So even if this thing, oscillates between two values again and again and again and again, it never quite settles on one converging value. If you take the limit as n goes to infinity of the positive piece of this, right, the non-alternating part, that ends up being 2n over n basically, or 2, which does not equal 0. The nth term divergence test proves this diverges. So the nth term divergence test proves this series diverges. That's it. Proves this series diverges. Notice that what we did not do here is we did not use the alternating series test for convergence. We noted that this thing is going to diverge. Even though our terms decrease in absolute value, they do not approach 0, and therefore this thing diverges, but not because of the alternating series test, because of the nth term divergence test. And that's a very common way that an alternating series will diverge, is with that nth term test. And showing that your final term doesn't equal 0. It's very hard to get a function to go to 0 eventually and not also decrease. There are types of functions you can do that with, but this is the more common way it's going to diverge. All right, give yourself a pat on the back, maybe a double pat on the back, and a high five. You rocked it. I wasn't so bad either, right? I will see you in the next video where we go over why the alternating series test makes sense. Stoked for that. Peace.